How we doing there, neighbor? Uncle Lee back at you, February 9th, 2015, with a little discussion on series. We're going to mostly talk about power series today. Before we start talking about power series, let's define any series. So what in the world is a series? Consider any series. A series is a sum. A sum from k equals 1 to infinity of a sub k. Let's fix our notation here. Of a sub k, which is equal to a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n for some integer plus dot dot dot. So how many creatures are we adding up there? We are adding up infinitely many things. So another word for a series is simply an infinite sum. A series is a sum, an infinite sum. It's hard for many of us, including me, to wrap our head around adding up infinitely many things. But that's precisely what a series does. So when we speak about series, we can call them infinite series, or we can just call them series. So when we say the word series, we mean infinite series. We're adding up infinitely many things. We're adding up from k equals 1 to infinity of some sequence, adding up an infinite amount of terms. So let us today talk about, specifically, power series and where they came from. And I will tell you that power series are pretty straightforward, not that difficult. Let's define a power series, and then we'll talk about where it came from. So, form A of the power series is simply going to be the summation from n equals 0 to infinity of c sub n x to the nth power. And I have c sub 0 x sub 0 plus c sub 1 x sub 1 plus some coefficient x squared plus dot 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 plus some coefficient, the nth coefficient of the x to the nth term plus dot dot dot. An infinite term. We're adding up infinitely many terms. These is just subscripting here. C, that's the coefficient. And we'll see down the road, we'll talk about some series that have different coefficients. But this is a power series because if you see the x part of the term, the x factor of each term increases by a factor of x each time. So we say this is a power series. This particular series is a power series. This particular power series is a power series centered at x equals 0. And we'll see in a moment why we're centering that at x equals 0. So this is the first and the most common for us at this level series that we're going to deal with. The most common power series is the power series centered at x equals 0. But we can also, and we will, but not a lot, we'll look at the series of form B, summation from n equals 0 to infinity of c some constant, the coefficient, of x minus a to the n. And what we have? The coefficient of the 0 term, x minus a to the 0, which is going to be 1, plus the second coefficient, c sub 1, x minus a to the first power. And you see we're adding those rascals up. Coefficient, x minus a to the first, coefficient, x minus a squared, plus dot dot dot, coefficient, x minus a to the nth power, plus dot dot dot. This we say is a power series. This is the power series centered at x equals a. Yes, if you notice that this thing is centered at x equals a, and we're looking at it x minus a, x minus a, x minus a. Down the road, we'll see what it means. What do you mean centered at x equals a? What do you mean? What? Well, we will be able to, and you will understand why we say this series is centered at x equals a. That's an easy thing to understand. Here are some important questions about series. Here are the questions that we're going to ask ourselves. Questions about power series. Does the series converge? Does the series converge? Does it converge? What do you mean? What it means for a series to converge is, does that infinite sum equal a real number? Does that, adding up those infinitely many terms, does it equal, that's hard for us to wrap our head around. But that's the question we're going to ask. Does that infinite series, does it have a sum? Does it equal something? That's what this question means. If so, where? What? Where? Does it converge everywhere? Or just on an interval? Maybe at the end points of the interval? Or just at a point? Those are some important questions about this series. Does the series converge somewhere? And this is a fascinating topic, believe you me. So, there's our definition of power series. We got your power series centered at x equals 0. Pretty straightforward. We're going to come back to this slide. We have the power series centered at x equals a. We'll certainly come back to this, to our definition of a power series. Now let's see where in the world these power series came from. To do that, we're going to recall the geometric sequence. Let's recall that geometric sequence right there. A sub n is equal to a times r to the n minus 1. We know what a geometric sequence is. We've spent enough time with geometric sequences. We've spent enough time on geometric series. And we know, and I've been preaching the importance of getting your head completely wrapped around the geometric series. Well, what is the geometric series? The geometric series is that infinite sum from n equals 1 to infinity of a sub r, a times r to the n minus 1, where a is the first term, r is the common ratio. This is the geometric series. And recall about the geometric series. Well, what can you recall about that geometric series? Does that geometric series, stepping out of the video, does that geometric series converge? Does that geometric series converge? And what we found out was that thing converged if that common ratio, if the absolute value of the common ratio was less than 1. This is huge. This fact right here is going to be huge for us. And if that common ratio, if the absolute value of that common ratio was less than 1, what do we know? We know not only that that infinite series converged, but we found out exactly what it converged to. And what did it converge to? It converged to this creature right here, first term divided by 1 minus the common ratio. Keep in mind that only happened if the absolute value of the common ratio was less than 1. Then this infinite series, adding up infinitely many terms, infinitely many outputs of that geometric sequence, headed to that guy right there. And then we've done enough examples. We're going to do another example right here. An example follows, and here's your example. This rascal right here. 0.3 plus 0.03 plus 0.003 plus dot, dot, dot. And we know what that's going to equal. That's 0.3 repeating. Hey, what's the first term? We discovered this, that the first term was 3/10. We didn't discover it. We found that out. The common ratio is 1/10. The first term was 3/10. So this is going to be the summation from n equals 1 to infinity of 3/10 times the common ratio of 1/10 to the n minus 1 power. And since my common ratio, 1/10, since that is less than 1, this thing did converge to 3/10 first term, 3/10 over 1 minus r, r 1/10, so that converged to 3/10, 1 minus 1/10 is 9/10, 3/10 over 9/10 is 3/9 and 1/3. That's why 1/3, and we found that out, that's why 1/3 is equal to 0.333 repeating is equal to 1/3. It's equal to 1/3. Why is that true? Because of that property of geometric series. That's a review. Let's go back to the definition of the geometric series. Here's our geometric series. The summation from n equals 1 to infinity of AR n minus 1. AR0 plus AR1 plus AR squared plus dot 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 AR n minus 1 plus dot dot dot. And we found out that this guy right here, this infinite geometric series, converge to A over 1 minus R if the absolute value of R is less than 1. The absolute value of R is less than 1. And look at this thing. Look at this guy right here. Look at that. AR0 plus AR1 plus AR squared, dot, 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 AR minus 1. If you look at that guy right there, what's the difference? Look at that and compare that to this guy right here. AR1, AR2, AR3, AR, they look oddly familiar, and they do. The difference being is here, these coefficients, if subscripting here, that means that those coefficients, they're not always the same. On geometric series, they are the same. Doesn't make that much difference. Well, it will, and we'll see that. But this looks very similar to, where were we here? This guy right here. Well, look what we can do. We can let's put a box wherever we see the common ratio. And we have A box 0 plus A box 1 plus A box squared plus A box cubed plus dot 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 A box n minus 1. Let me hide this for a moment so you don't look ahead. Plus dot dot dot, and that's going to equal, when does this infinite series there, when does that guy there equal A over 1 minus box? When is that true? When is that true? Think about that for a moment. Wrap your head around that. A box 0 plus A box 1 plus A box squared, dot, dot, dot. When is that true? When, and only when, does this guy here converge to A over 1 minus box? It's a geometric series because I'm increasing by a factor of box each time. Think about that. Well, hey, the box, what do you mean box? Box, box, box. Well, let's put an X in the box so we can think about it. The box, we can't wrap our head around a box, but let's put our X in the box. Let's put an X in the box. So now I have AX0 plus AX1 plus AX squared plus AX cubed plus dot 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 AX n minus 1. Now look at that guy right there, and compare that with this guy here. Now I got my boxes of X0, X1, X squared. Oh, now it even looks closer. Nice. Nice, nice, nice. So I got my box in there. Oh, I wrote on something. Oh, now you tell me. This is a geometric series. This is geometric. Homeboys, it is geometric. Because each term is increasing by a factor of x. I have the first term, and what's different between this and the power series that I talked about was that, hey, all these coefficients are going to be the same. When does this equal, when does that equal A over 1 minus x? Think about that. You tell me, when does this thing here equal A over 1 minus x? When is that true? When is that true? Pause the video and think about that. And now we come back. And yes, you are completely correct, absolutely correct. This is true. Whoa! This is true. Yes. When the absolute value of x is less than 1. It's geometric, is it not? Yes, it's a geometric series. Geometric series converge when that common ratio, when the absolute value of the common ratio is less than 1. It's that simple. This thing right here converges to a over 1 minus x when the absolute value of x is less than 1. This is huge. It's not that difficult if you have your head wrapped around the geometric series. And oh, I can solve this inequality. The absolute value is less than 1, so then when x is between negative 1 and 1. This is going to be important. This is important. And x is between negative 1 and 1. So, let's see here. Oh, let's see here. So, okay, so now, here's what we're going to do. And the A's for elementary math students, as we all are elementary math students, this A, let's do something really nice here, and let's just let A, let's see where we are. Where are we? We're right here. Everybody relax. Oh, I think where are we? We're right here. I think we're down here. Oh, we're going to put X in. Sorry. Hey, you know what? Let's make A 1. Let's make that A 1. So let's just relax. Let's look at this dude right here. AX0, AX1, AX2. Let's let A equal 1. That's the first term is going to be 1. It's still going to converge when the absolute value of x is less than 1, when x is between negative 1 and 1. And if we do that, 1 plus x squared, all these a's are 1, that's a very nice power series. First concrete power series that we can wrap our heads around. This, what's the R? What's the common ratio? It's geometric. The common ratio increases, the terms increase by a factor of x. This is a geometric series. We're also going to call it a nice power series because it fits the definition of the power series. If you look at the slide at the definition of power series, all those coefficients this time are just going to be 1. Oh well, they can still be all the same. And what is this guy right here? What's another word for this power series? Couldn't you call this? What would be wrong with calling this an infinite polynomial? That's what it is. An infinite polynomial. This is a 4-term polynomial. 5-term polynomial. ... An n-term polynomial. That converges if x is between negative 1 and 1 to 1, which is A now is 1 over 1 minus x. You've got to be kidding me. So I've got this infinite polynomial that's equal to this rational function, this simple rational function that we can graph, and we know that has a vertical asymptote at 1. This is a rational function equaling a polynomial is equal to this rational function, yes. What are polynomials? Smooth and continuous. They're easy to work with. Rational functions have this infinite discontinuity and we don't know about it. Easy to differentiate, easy to anti-differentiate. Oh, I can differentiate, it's hard. Not really, but you're going to see some that are hard. But let's look at this. What does this mean? Let's look at this graphically. I've got this polynomial that's equal to this infinite polynomial that's equal to that. Keep in mind, when is this true? This is conditional, what they call conditional equality. It's conditional. What condition? When is this true? What condition is this true for? When is this true? What condition? This condition, when x is between negative 1 and 1. This is the condition that has to happen for this polynomial to be true. Let's look at it on the graphic calculator. Bam! Here I have, I'm not going to look at this one, here I have that fifth term polynomial, and I have that rational function. I'm going to look at that graph. And something magical is going to happen. It's not magic, it's math. Awesome math. Here comes that fifth term polynomial, that fourth degree polynomial. And here comes the rational function in red. Oh! Well, here's the vertical asymptote of that rational function sketched in red. But look at this. Look what happens between, I've got my x window from -3 to 3. Look what happens between -1 and 1. Oh, the red curve is almost exactly the purple curve. Keep in mind, I only have 5 terms of that polynomial. Let's add a couple terms to that polynomial. This is amazing. Let's add a couple terms to that. Let's turn that guy off. Let's get down here. And if you notice now I have an 8-term polynomial. I have a 7th degree polynomial. And I'm going to graph the rational function is going to be in red. The 8-term polynomial, the 7th degree polynomial, is going to be graphed in black. And keep in mind, when are these things needs to be an equal? There's the rational. Vertical asymptote of 1. Here comes the polynomial. Here it comes. Here it comes. Did I turn? Yeah, I did. Here it comes. Here it comes. Look at that, girls. Look at that, boys and girls. Between -1 and 1, now it's even closer. Now the polynomial is even closer. Can I put my calculator, can I put infinitely many terms? No, I cannot. But I can be assured that if I could, between -1 and 1, that infinite polynomial would converge, if you will, to that rational function. And here's something else that I want you to start looking at. If I go up to my table, and let's just start at 0, and let your increments of 1/10. Look at this. If I go 1/10 away, exact. 2/10 exact. 3/2, I got this little error between the rational function and the polynomial. I got this error of, and look here, I got this error here. That's where the error starts. We're going to be looking at the difference between the power series and whatever the power series represents. Whatever function, in this case, that rational function. This is going to be important down the road when we start talking about the errors. So let's go back. Infinite polynomial. This is good stuff. Absolutely good stuff. Guess what? I could put, how did I create this? What did I do? I let A be 1 and I put X in the box. Guess what you can put in the box? Guess what you can put in the box? You can put anything you want in the box. You can put anything you want in the box for this geometric series. I put X minus 3 in the box. Guess what this is? This is a power series that's centered at, here's the box, here's the common ratio, this time is X minus 3. When does this thing converge? It's still going to converge to A over 1 minus box if box, or X minus 3, is absolute value of X minus 3 is less than 1. I solve this inequality. This inequality produces 2 is less than X is less than 4. Hey, what's the center of 2 and 4 at the interval 2 and 4? 3. That's why we say that this power series is centered at 3. At this, we will have a power series part 2, but power series part 1. Let's just worry about those power series centered at 0. And how did I get it? How did I get it? All I did was put 1 in for A and X in the box. Don't forget, this is my geometric series. all I'm doing is putting some x in for the r, and that's going to give me my first power series, which is this guy right here. And keep in mind, this is something else. If this is true, and this is true when x is between -1 and 1, this is conditional equality. An equality that this is true for. Keep in mind, if it is true, then I can use all of the properties of equality. Multiply both sides by the same thing, subtract both sides by the same thing, and we will manipulate this inequality as we go. Thanks for listening. Thanks for showing up. Power Series 101. Bon,